Welcome back. In this video, we'll continue talking about chapter 24, simulating normally distributed random variables. No mini exercise in this video, but let's get back into it. Remember in the previous video, we used the norm.inv function, norm.inv, to simulate a normally distributed random variable, right? And we'll use that to simulate market returns and extend it today. So in this video. So recall in the previous video, we simulated something between 0 and 1 using the RAND function, right? The RAND function gives us a uniform distribution between 0 and 1. That corresponds to like a percentile. In other words, if we treat 0.3599 as like a randomly simulated percentile of a normal distribution, like the 36th percentile. What's the 36th percentile of a normal distribution with a mean of 0.69% per month, right? Which is the historical monthly average return for the S&P 500. And then a standard deviation of 4.12%. Well, that corresponds to a return of negative 0.784%. So let's build that into a simulation model where instead of just one simulated return, we'll simulate 12 monthly returns and then compute the total return, okay? So let's do that. Remember, equals norm.inv is how we simulate a normally distributed random variable. The randomness comes from the RAND function, some random number between 0 and 1. And then let's specify the mean of our simulated data. I'll make a cell reference to the mean, and I'll make that absolute with F4. And then the standard deviation is here. Thanks for your patience. The standard deviation of the distribution of our Monte Carlo simulation is going to look like this, right? So simulate some random number between 0 and 1, and given the mean and standard deviation of a distribution, return like the value of that variable. So here's a monthly return that's well above the mean, right? 5.787% in a given month, which is much higher than the monthly average of 0.69% per month. So let's copy and paste this over. And what we'll end up with, let me just check. Yeah, our cell references stay where they're supposed to be. Here's 12 monthly returns simulated from a normal distribution, right? So if we assume the monthly S&P 500 return follows a normal distribution, we can simulate based on a normal, using the norm.inv function. And what do we do with this, right? I guess we could find the mean. This monthly average comes out, this average across these 12 months comes to be 2.4%. We could also find the total return. Let's do that. And to take the total return, right, to compound these returns, we would take 1 plus each of them and multiply that, right? 1 plus negative 0.01269 times 1 plus 0.0292 times 1 plus 0.0343. And so there's a great array for, we could use the product function. And if we enter it as an array, product of 1 plus all of these, and then subtract 1 at the end, that'll compound these returns. So all of this first simulation of 12 months of returns comes out to a total return of 6.24%. Let's copy and paste this down and use this to illustrate what we do with simulated data, right? So in each simulation, I'm simulating 12 months of returns. I'm compounding them to get the total return across those 12 months. And then we'll do that 100 times. And what's the point of this? The nice thing about Monte Carlo simulation is that you get a range of possible outcomes, right? I can see what the worst simulated 12-month return is based on my data and the best, and then the percentiles, right? So to figure out what percentile each of these, so like what's the 10th percentile of this range of simulated outcomes? That's one of the benefits of simulation. So equals percentile. There's two percentile functions, percentile exclusive, percentile inclusive. Feel free to check out the differences if you're interested. They should be mostly the same for a large cell range. But the percentile function The first argument is the range of data that we want to look at. And the second argument is the percentile. So if we put in this function, this gives us the 10th percentile of our simulated returns. In other words, if we ranked all 100 simulated like outcomes from worst to best in terms of total return, right, the 10th worst one is negative 7.678%, right? And then the 25th percentile comes out to be negative 1%. The median is here, 50th percentile, and the 75th percentile. So the great thing about Monte Carlo simulation is you get a range of possible outcomes. So in this video, we simulated normally distributed returns, and then we also compounded them, and then we illustrated how to use the percentile function to see the range of outcomes for our simulations. So in the next video, we'll continue to extend this and build sort of a portfolio simulation model that hopefully will be, you'll see the relevance of it. Thanks for tuning in.